Okay, so welcome back from the break, or not the break, the weekend, grade 11s and 12s. So we have really this lesson left and then next week's lesson. Now this lesson will have a learning check attached to it, but next week's lesson won't. So this is kind of the completion of, turning in all your learning checks, and I'll mark all the learning checks that get completed by Sunday. And then next week I'll present material, but there won't be a learning check. Now it's still important, especially for those graduating as well as going into the advanced chemistries next year, that you still kind of look at the lesson next week. Okay, but there just won't be a learning check attached. So this week we're going to kind of go through acids and bases. So these are very, very common thing we talk about in chemistry. Basically, when you look at a liquid, any liquid is considered either an acid or a base. Okay, now there is something called that's neutral, and that's at a pH of 7, which would be something like water, but that's the only thing that's neutral. Anything other than water is going to be either considered an acid or a base when you look at it as a liquid. So let's go through these two things mean. So just some background about why acids and bases are important. We use them as products all the time. And a big part of chemistry is the creation of acids and creation of bases, because a lot of the products that we use are one or the other. So acids and bases have been used for thousands of years for a variety of purposes. One of the first acids widely used was vinegar. Okay? Vinegar is basically a digestible acid. It's something that we can get nutrition from, and it can help preserve our food. So vinegar could be used to season food, so we put vinegar on food. It's a disinfectant for food as well, okay, because this acid is not strong enough to hurt us, but it's strong enough to basically burn bacteria or burn virus away. So that's how it disinfects food. That's a very powerful cleaner, so you can use vinegar to clean things as well. And it's also a rodent deterrent, okay, because rodents also don't like the taste of it because it's so acidic and it kind of burns their tongue. So that's a very, very popular acid that we use. Okay, vinegar is also known as acetic acid or glacier acid. Okay, there's just two other names for it. Now, one of the ways that we use bases, and you use bases all the time, especially now with the coronavirus going around, is soap. Okay, all soap is basically a base, and for the same kind of reason that acid can kind of burn, small living organisms like bacteria and viruses, bases can also kill them. Okay, so we use bases in our soap, and that's what helps us disinfect things as well. Okay, so those are two examples. Now, kind of more recently, acids presently are used for a variety of important and chemical processes. They're often used as a catalyst to speed up reactions, so sometimes we put acids in just to make another reaction go quicker. Acids are also used to produce fertilizers, to make plastics, to make cars. A lot of explosives are acidics. A lot of the pharmaceuticals that we take are acidic, and that's why sometimes they'll upset our stomach, and many other purposes. So acids are very, very common in our products. Now, bases are a little bit less common. We don't see as many bases in our products, but there is still some important ones, such as the pulp and paper industry, and those are kind of the telltale ones. A very, very popular base used in industry is called sodium hydroxide. Okay, and if we remember the name properly, okay, let me just write this out. We'd have sodium and then hydroxide. Okay. All right. Now, some differences between acids and bases, or again, just some more examples of the two types. So acids and bases are an important part of a group of solutions. They are used in many industrial and household products. Acids and bases have different unique properties. So if we look at kind of some examples of acids, okay, these are things like citric fruits. So a lot of the fruits that we have an acidic component to them. Almost every fruit that you do is either highly acidic, like say a lemon, or slightly acidic, but we do enjoy the taste of that, like an apple or an orange. Okay? Batteries are all made out of acids. Soft drinks. Okay, what soft drinks are is you take carbon dioxide and dissolve it into water, and that makes carbonic acid. And that's why you kind of have that little burning sensation in your mouth when you drink a pop. Vinegar, again, is another telltale sign. Bases are a little bit less, familiar with us. So things like antacids, okay, and those are things that people who have acid indigestion in their stomach will take a base to neutralize it. Ammonia, also a base, drain cleaner. Blood is slightly basic, and baking soda. That's probably our most common base that we see all the time. All right, now, a very, very important slide here, and this is the properties of acids and bases. So being able to identify them and kind of know how they're going to behave. So if we look at the first thing, say electrical conductivity, okay, well, both of them can conduct electricity. So that's really not a really beneficial way of discriminating between the two. Okay? But the ones that I've highlighted in yellow are the differences between the two. Okay? So the feeling of the solution, when you put these things on, when you put an acid on your hands, you don't really feel anything different than, say, water. You may feel that it's wet, but you don't really feel anything unless you know it's obviously a strong acid and it starts burning you. But just a regular short acid like vinegar, you put that on your hands, you don't feel anything. But if you put a base, like something like sodium hydroxide, which you should not do, but if you did get it on your hands, it's very, very slippery. And that's why soap is slippery, because soap is a base. So that's a big difference, is if you touch it, you'll know the difference. Now, that's not a very safe way of determining whether it's an acid or a base. Along with the next one, it's also not a very safe way of doing it. But there is a difference, is if you taste either of them, acids generally taste sour, where bases taste bitter. Okay? So the difference between the two tastes is a telltale sign. Now, this is how we usually test for it, is the reaction with litmus paper. Okay, there's a certain type of paper that responds differently to whether it's an acid or a base. Okay. So with litmus paper, it will always turn the litmus paper red, okay, if it's an acid. So whatever color the litmus paper is, whether it's blue or it's already red, it will remain red if it was already red, or it will turn a blue litmus paper to red. And base is the opposite. Okay, it's going to turn everything blue. So if you have red litmus paper and you drop it into a base, it will turn blue. Okay, and if you have blue, it'll remain blue. Now, some other differences, ways to identify them, but this causes us to start doing some reactions, which is not easiest way to identify an acid or a base. We'd always use litmus paper or a pH scale. It's the reaction with metals. So acids usually react with metals, okay, where bases don't react with metals. Okay, and carbonic compounds, so compounds that contain carbon, usually react with acids, and there's no reaction with bases. Okay, now this is just going to briefly get into the two theories of how acids and bases work, because we should know at least on a very high end of the difference between the two. So there was really kind of two theories. This is the first theory, which is very, very common. It's where most people would say acids and bases. If you're going to do junior chemistry or very simplistic chemistry, this is the theory that you go with. But as a real chemist, you should know the second theory, which is way more accurate, but it's just a little bit hard to explain to the average non-science person, so we sometimes stick with the first theory. So we're going to go through the first theory first, and this is where you may think of an acid or a base. So the first theory, when they looked at acids and bases, what they basically said, okay, an acid is a substance that basically produces H pluses. So anything that makes an H plus when it goes into water is going to be an acid, and a base is anything that makes an OH when it goes into water. So an example would be like hydrogen chloride. Let me just write this out here for you. So it would be like HCl plus water going into H plus Cl negative. Okay, so it produced an H plus, so that means it's an acid, and that's where the H plus came from. It's HCl. Where a base was something like sodium plus water into sodium hydroxide, and the fact that I produced an OH, okay, tells me that I have a base. Now this is really kind of the way that most people identify acids and bases. They say acids are H pluses and bases are OHs. So most cases, if you want to identify a base, it'll have an OH in it. And most cases, when you want to identify an acid, it's going to have just an H in it. But that doesn't work for all of them. And that works for most cases. Chemists, we had to have more of an accurate view. And this is the more updated view of the difference between an acid and a base. An acid is still a substance that makes an H plus, so that hasn't changed. However, what has changed is a base doesn't always have to be OH. Okay, you can have a base that doesn't have an OH in it. So they've described a base as basically something that accepts the H plus. So every time you have these two liquids react together, one of them is going to release the hydrogen and the other one's going to absorb the hydrogen. So in every single time you have two liquids, one's an acid and one's a base. And I know that sounds a little confusing, but I'll kind of give you an example coming up. Okay? All right. So just in the new theory, and this is the kind of the chemist theory of acids and bases, all acids must contain an H in its formula. Okay, therefore, all acids contain hydrogen. They need to because, by definition, they have to release that hydrogen. So every acid must have an H in its formula. Okay? But the big difference in this more accurate chemist view of acids and bases, a base does not need to have an OH. It can be any negative ion willing to accept hydrogen. Okay, so let's look at it kind of an example. So here we have a reaction. Okay, and let me just shrink my size down here. And we have HCl reacting with water to form what we have over here. We'll talk about that in a second. So this is on the reactant side. And on the reactant side, there's always going to be both an acid and a base. So we have to basically figure out, well, which one is this? Is this the acid or is this the base? Right, so on the left-hand side, either HCl is going to be an acid or a base, and water is either going to be an acid or a base. Well, we know by definition, an acid is the one that donates the H+. And in this case, okay, if you look over here, the chlorine is not attached to the H anymore. Basically, what has happened is this H has come off, okay, and then has joined with water to make a hydronium compound, or H3O. So what has happened is, since HCl has donated the H+, we call this the acid, because the H+ came off of it. Okay? Now, since water is the one that picked up that H+ and then eventually became this, okay, we call this then the base. So whatever molecule, whatever reactant is going to absorb the H, and in this case, water absorbed the H, that becomes the base. And whatever reactant releases the H, that is, we call the acid. So in this case, HCl is the acid and water is the base. So again, over here we've got acid and we've got base. But what we haven't talked about is what these things are. Right? These things over here, the products. So what do we name them? If we call this an acid and we call this a base, what are we going to call these? Well, these have also special names. Okay? The products contain special names, and they call them conjugate acids and conjugate bases. We have to use this word conjugate to indicate that it is the product side of an acid and base reaction. Okay, so which one's conjugate acid and which one's conjugate base? Well, we're going to go through it right here. So here's our kind of reaction again. I'm just going to write out, this is my acid, and this is my base. And we want to figure out, well, what's this thing called and what's this thing called? Well, when two molecules or ions are related by the transfer of a proton, like H+, like the example above, okay, and the H positive just is transferred, they are called conjugate base pairs. Okay? So this is the important part right here. The conjugate base, okay, is what remains after the acid loses its proton. So here's my acid, okay, HCl. I lost my H+, and I became Cl-. Okay? Well, we call this the conjugate base. Okay? It's what's left after the acid, and this was the acid, loses its proton. Okay? So we call that the conjugate base. And we call the other thing, the H3O in this case, the conjugate acid, because it's what remains after the base absorbs the proton. So after water, which is the base, absorbed H+, it became this. So we call this the conjugate acid. So the big thing that I want to get across from this lesson is that you can look at a reaction like the one that I have shown here and be able to identify the acid, the base, the conjugate acid, and the conjugate base. So let's kind of give an example. Before we do that, we'll just kind of just summarize. Every acid contains a conjugate base, and every base contains a conjugate acid. Okay? So to identify the conjugate acids and bases, this is what we're going to do. This is kind of the whole goal of kind of this lesson is to be able to do that. Is you have to locate the acid, then the conjugate base has one less hydrogen than that acid. And the second part, you locate the base, and the conjugate acid has one more hydrogen than the base. Okay? So I know it sounds confusing, so let's give it an example. So here, we got hydrogen bromide gas. So hydrogen bromide, okay, and it's a gas, is bubbled through water. Okay, that's going to be a liquid. To create hydrobromic acid. So we basically bubbled this through water and we create hydrobromic acid. So what that's going to result in is we are going to have, so in this case, we're going to have this hydrogen. It's going to come off, okay, and it's going to join with the water and make H3O. It's going to have a positive charge on it. Okay. Now, what's left, since this hydrogen left and went and joined the water, okay, the only thing that's now left is my bromine ion. Okay. So this is the full reaction that we have here. Now we have to identify the acid, the base, the conjugate acid, and the conjugate base. Well, by definition, okay, the acid and the base are going to be on this side, okay, and the conjugate acids and bases are going to be on the product side. So let's start with the easy part on the left-hand side. Which one of these kicked off a hydrogen? Well, between these two molecules, water or HBr, we can see that HBr is the one that kicked off the hydrogen. So we call this the acid because it's anything that donates the hydrogen. And we know that water picked it up. So we call this the base. Okay. Now going across here, okay, the conjugate base is going to be what's ever left over after the acid. So HBr, this was the acid, it lost, and whatever's left over, which is the Br negative, this is now going to be the conjugate base. And the base that picked up that H plus, it picked it up, and now it becomes the conjugate acid. Okay, so that's the kind of the lesson this week. It's a little bit shorter, but again, we have one more next week, and then the course is done, and I'm sure everybody will be pretty happy at that point. Okay, thanks, guys.